Okay, so hello everyone. So in the earlier plan space, we have actually discussed about the continuous blending system and come up with components balance of this. Correct? We remember that X1 and W1 is one of the inlet, and this is the second inlet, and we have only one outlet. So this is the component balance that we get. So today, we are going to do a transfer function model for this system, a similar system. Okay, to start off, we'll make a few assumptions. Okay, so this is to simplify our job. Okay, then we would assume that the density of liquid, volume of liquid, mass flow rate 1, mass flow rate 2, and final mass flow rate. And at the same time, x2. All these we assume as constants. Okay? So you'll notice that we can actually move it out, and we'll have this equation now. Okay, so we define this as equation 1. Okay? So notice that now x is the output and x1 is the input. Remember this because it will be important for us at the end later. Okay, so what we do now is that we continue with the step 1, that is to define at steady state. Okay, so for this equation, okay, we start off with here. At steady state, dx over dt is equal to 0. So we put a big 0 for it. W1 is a constant and x1, it is a variable. So at steady state, we denote it with a bar. And these are all constants. Okay, notice that x is also a variable and there is a bar here. We call this equation 2. What we do now is we take equation 1 minus equation 2. So you should get this. And you can just put it all in. This 2 shall cancel off. And you get this. Okay, so it's a bit confusing. I mean, it's too much information here, so we simplified it using deviation variable. We define them as deviation variable. Okay. So what we do here is we do it this way: x1 prime is equals to x1 variable minus x1 at steady state. The same goes for x. Okay, so now the equation 2, okay, we copy back the earlier equation, which is this. Okay, and after putting in a deviation variable, you should actually get this. Okay, so this we define as equation 3. Okay, so now we have all this. Yeah, notice that x prime and this is still x. So we want to change this here. And we define it like this. Correct? And at steady state is equals to 0. So it's equals to dx over dt. So dx prime is equal to dx over dt. We can actually put this thing here into here. So at the end, we should have this. And this is equation 4. So what we like to do now is to transform this entire equation using Laplace transform. Okay, I think I'm running out of space. So Laplace transform for this equation. You should get this. Okay. So rho v is a constant, we just take it out. And for here, this is just a basic Laplace transform. I think you can just check it out anywhere. And W1 is a constant. And x1 is a variable. So it will be transformed. Same goes here. Okay. sorry, there's a prime here. Yeah. So we assume this system to be at nominal steady state. Okay. Again, it's another assumption. So what we do here is this. It means that at steady state, this x is actually equivalent to x bar, okay, because it's steady state at initial condition. So when x bar minus x bar, you get a 0. So x prime 0 equals 0. You can just take this out. Okay, so we get this. Okay, you see this? So remember earlier which one is the output variable, the x, and the input variable is x1. So what we're going to do here is to derive a transfer function model, which is GS, where you get the output over the input. Okay, so if you rearrange the earlier equation, you should actually get this. It's just a simple rearrangement, no rocket science around here. Okay. So we want to do it in this way, output over input, you will get this. Okay, so after rearrangement, you should get this. So it's a bit confusing here, so we will simplify it this way. Okay, so if you put all this in, you should get this. Okay, and this is the one that we're looking for today.